Today we are going to discuss the principles of clasp assemblies. It's important to have a good grasp of these principles as clasp assemblies contain four component parts of the partial denture. We need to cover these principles prior to attempting to design the removable partial denture. They are very important, though, to the success of the final prosthesis. Pictured here is a clasp assembly. It must be made up of four component parts of the partial to be effective. It's responsible for the retention that exists on the partial denture. It has a direct retainer. It is impossible to tell which of those two clasp arms on the clasp assembly is the direct retainer, but the direct retainer is the one that engages the undercut below the height of contour on the tooth. It also contains a rest, a reciprocal component, which is the arm on the opposite side of the tooth from the direct retainer, and a minor connector, which is the distal guide plate on this illustration. We'll review a little bit of your terminology now before we discuss the principles of clasp assemblies. The direct retainer is any component part of a removable partial denture that engages an abutment tooth in such a manner as to resist the displacement of the prosthesis in an occlusal direction. The direct retainers can be on the buccal or the lingual surface of an abutment tooth. They may take many forms, which we will see later in our discussion. The rest is used to designate any component part of the partial denture that is placed on an abutment tooth in a prepared positive rest seat so that it limits the movement of the denture in the cervical direction and transmits the functional forces to the abutment teeth. The stabilizing component, by its reciprocal action, resists the horizontal stresses placed on the abutment tooth by the retentive arm of the clasp. As that retentive arm flexes in order to get into the undercut on the buccal surface of the crown, the reciprocal component stabilizes the tooth and prevents movement in a lingual direction. The stabilizing component may be an arm or it may be plating as shown in the pictures above. The minor connector arises from the major connector. It unites the major connector with other parts of the removable partial denture, such as rest, indirect retainers, direct retainers, and base. The example of our clasp assembly, the guide plate actually connects the major connector with the rest. It's considered a minor connector. A removable partial denture needs sufficient retention to resist being dislodged in a vertical direction. There are two types of retention involved. One is primary retention, and it is achieved by placing direct retainers on the abutment teeth used for the partial denture. The second is secondary retention, and it's produced by close contact of minor connectors with the tooth guide planes and with denture bases and major connectors in intimate contact with the underlying tissues. There are two different types of direct retainers, and they're shown on this slide. The upper and the lower left picture show an example of the intracoronal attachment. That means that the attachment is completely confined within the crown of the tooth. The pictures on the right show the extracoronal attachments. They are placed on the outside of the crown. The upper is an ERA attachment, and a nylon nail is placed in the partial denture base. The lower shows a conventional circumferential cast clasp. They are placed on the outside of the crown and are cast with the metal framework of the RPD. Here's a close-up of the intracoronal attachment. It is also called an internal or precision attachment. The thing that makes it a precision attachment is that it is milled with precision instrumentation, and then it is caught into the framework when the framework is cast to it. It can also come as an independent part that is picked up in the acrylic resin when the partial denture is processed. It's easier to correct any problem that may happen when the attachment is caught in the acrylic. The components of the intracoronal direct retainer are 1. The matrix, sometimes called the female, which is a metal receptacle contained within the normal clinical contours of the crown or the fixed restoration. The other part is the matrix or male, and it is the component that is attached to the removable partial prosthesis. The combination of the two serve to retain and stabilize the prosthesis. When more than one of these are used in a prosthesis, the two must be perfectly parallel to one another and to the path of insertion of the partial denture, or they will not work. A surveyor is often used to create these two attachments within the prosthesis. Intracoronal retainers can be divided into two different categories too. Pictured on the left are the components that are fabricated in metal using real high precision manufacturing techniques, and those are called precision attachments. The other are components that are fabricated with precise fit that are termed semi-precision attachments. Now, they often originate from a wax or a plastic pattern that is cast into metal. The extracoronal direct retainer uses mechanical resistance and is placed on or attached to the external surface of the abutment tooth. The extracoronal attachments shown on this slide vary from one another. The far left shows a cast circumferential clasp that are created with a wax pattern and then cast into the framework. The other extracoronal attachment comes as a plastic pattern that is placed onto the crown's wax pattern and then cast. The plastic patterns that are cast are not as precise as those that are milled and are classified as a semi-precision attachment. Also, the male part of this one is nylon and much more flexible than a precision attachment, which would be milled metal. It is easily replaced, though, if something goes wrong. The extracoronal direct retainers can therefore be divided into extracoronal attachments and retentive clasp assemblies. These are the three most common attachments that we have used around the ULSD in recent years. They are the Noble Biocare ball attachment, O-rings, and the locator attachment. We are using the locator now in our 2 implant retained complete denture cases and in our RPD implant reconstructions. The advantages of the internal attachments over the external attachments are: 1, they eliminate unsightly retentive arms on the teeth, so they're very aesthetic. 2, they direct the forces through the rest seat area, which is in a more favorable position to the long axis of the tooth. There are more disadvantages of internal attachments than advantages. 1, they're complicated clinically, and the laboratory protocol is also complicated. They often require cast restorations. They're very difficult to repair and replace when something goes wrong. They will wear with time. The effectiveness is directly related to the length in the tooth. They are difficult to place in the confines of a natural tooth without over-contouring it a bit. They're much more time-consuming, and they're very costly for the patient. The internal attachment should not be used on large, long distal extension areas of removable partial dentures, unless some form of stress breaker is used between the attachment and the movable base. They place more torque on the tooth than the external attachment. To properly design an RPD, the dentist, not the laboratory technician, must consider the path along which the prosthesis will be inserted and removed from its terminal seated position. Upon insertion, the clasp arms will contact the axial surfaces of the abutments. With continued seating, the retentive arms will flex as they pass over the height of contour of the abutments. As the clasp assembly is seated, the direct retainer will be active. It will return to a passive state when it is completely seated past the height of contour. This motion places the retentive terminal 1/3 of the direct retainer into an undercut relative to the path of insertion. The Dental Surveyor is the only reliable method of analyzing teeth well for determining the retention on the RPD. The dentist uses the Dental Surveyor to determine the path placement. It is the relationship of the vertical arm to the cast. It is the path that the partial denture will take as it is inserted and removed from the mouth. By changing the path of placement by rotating the cast on the table, you may not have an area of undercut like you did at the first position of the cast. The location and the depth of the undercut is therefore relative to the path of placement as determined on your surveyor. The height of contour is defined as a line encircling a tooth at its greatest circumference. It is determined by the dental surveyor. Think of the Earth as a globe, and the equator would be the height of contour. It is the place where you have the greatest circumference on the globe. The undercut is that portion of the tooth which is between the height of contour, as shown by the survey line, and the margin of the gingiva. Another name for this area is infrabulge or retentive area. The support area is that area of the tooth which is occlusal to or incisal to the height of contour, as shown by the survey line. Other names for this area are non-retentive area or suprabulge when on axial surfaces. The angle of cervical convergence is the angle viewed between the vertical rod contacting the abutment tooth and the axial surface of the abutment. Its apex is at the height of contour. Anything below that area is into an undercut on the tooth. The factors that determine the amount of retention a clasp may have are 1. The size of the angle of cervical convergence, in other words, the depth of the undercut. Secondly, how far into the angle of the cervical convergence will the clasp terminus be placed? And 3, what is the flexibility of the arm that's going to be placed into that undercut? Let's say that we are going to use a cast circumferential clasp on this tooth. For ideal retention, we will place the terminal 1/3 of that clasp arm into a .01 undercut. A couple of conclusions you need to make about the angle of cervical convergence are: 1. The less the angle of cervical convergence, the farther away from the apex of the angle, or the height of contour, the .01 undercut will be. Conversely, the greater the angle of cervical convergence, the closer to the apex or height of contour the .01 undercut will be. Certain areas of cervical convergence may not be usable for retentive purposes. If at the point of .01 undercut that arm impinges on the gingiva, that prohibits placement of a direct retainer at that point. We sometimes have to alter the tooth undercut in order to place the clasp into a proper position. We sometimes place restorations like crowns on the teeth to achieve a good position in the cervical 1/3 for our direct retainer. In summary about retention, the location and depth of a tooth undercut or retentive area exist only at a specific given path of placement and removal of the partial denture, as shown with the dental surveyor. Also, the non-retentive areas of a tooth on which rigid components are to be placed exist only for a given path of placement of the cast in relation to the surveyor. The most suitable path of placement is generally considered to be the path that the partial will take where it requires the least amount of mouth preparation to place the component parts in their most ideal position. Forces that attempt to dislodge the partial are usually off vertical forces. Therefore, the path of insertion and removal should be as perpendicular to the plane of occlusion as possible. There are two basic types of clasp assemblies. The cast circumferential or suprabulge direct retainer approaches the retentive undercut from an occlusal direction. sometimes called an Akers clasp. There's also a vertical projection or a bar type or infrabulge direct retainer, which approaches the retentive area from a cervical direction. It's also called a roach clasp. Now, it may help you remember which one's an Akers and which one's a roach if you kind of picture that little eye bar as a roach clip, which I'm sure some of you know exactly what I'm talking about. A clasp assembly can be a combination of cast circumferential and bar clasp, or it could be a cast circumferential and a wrought wire, so that it can be a combination of the two. The Suprabulge clasp arm can be divided into three segments. The section of the clasp that originates from the minor connector is known as the shoulder and is given the letter A. The portion of the clasp that crosses over the height of contour, or the survey line, into the 0.01-inch undercut is referred to as the terminus, and it's shown with the letter C. It is usually in the terminal 1/3 of the clasp arm. The area between the two is referred to as the middle section or mid section, and it's shown with the letter B. The infrabulge clasp arm consists of two segments. The approach arm, which is a minor connector that originates from the framework and travels horizontal to the mucosal surface and turns vertically upward at the middle of the tooth. It crosses the free marginal gingiva at a 90-degree angle. The terminus arises from the vertical portion of the approach arm and engages a measured undercut of 0.01 on the surface of the abutment. It extends a minimum of 2 to 3 millimeters upward from that 0.01 undercut, so it touches the tooth as a pod and not just a point retention. To refresh your memory, the clasp assembly consists of the direct retainer, the rest, the reciprocal component or stabilizing component, and a minor connector. When talking about clasp assemblies, we cannot lose track of the importance of the minor connectors. Minor connectors may serve as 1. A plane that guides movement for the insertion and removal of the partial, 2. A reciprocal element to counteract non-axial forces produced by the retentive arm, such as the strut leading up to a rest, and an approach arm for the infrabulge clasp. We are going to develop planes on the sides of the abutment teeth next to the edentulous areas that guide the partial denture into position. Guiding planes can be prepared parallel to one another and parallel to the path of insertion. These parallel guiding planes control the path of placement and removal of the partial denture. They provide additional retention by limiting dislodgement because of the stability of the partial denture. Without the guide planes, clasp retention would sometimes either be practically non-existent or very detrimental to the health of the teeth because of the movement that would take place by the removable partial denture. The retention created on all the abutments should be as equal as possible. The retentive arms will be placed into a measured undercut of 0.01 or 0.02 inches depending upon the type of clasp used. It will be placed regardless of the distance below the height of contour. The position, though, is influenced by the angle of cervical convergence below the height of contour. The clasp assembly must have the following attributes to have good retention. The direct retainer must provide retention for the prosthesis. Only the terminus is placed into the undercut. The rest must support the clasp assembly so that the retentive component is secured in its desirable position. The minor connector must be rigid and provide stability for the prosthesis. This is the charge of the guide plane and the minor connectors leading to the rest. Reciprocation must be present to keep movement of the tooth from occurring when the direct retainer flexes into the undercut. It should contact the tooth slightly before the direct retainer to brace the tooth. The clasp assembly must exhibit encirclement of the tooth to prevent the tooth from moving away from it. and when the prosthesis is finally seated, the clasp assembly must be passive. It should not be placing forces upon the tooth in any direction. Retentive clasp arms are the most common way that direct retention is achieved. The flexibility of the retentive arm allows the direct retainer to cross over the height of contour of the abutment tooth and settle into an undercut of a measured amount that is appropriate for the type of metal used and the choice of clasp that has been determined in the design by the dentist. It does so at a chosen path of insertion for the prosthesis that is determined by the dental surveyor. The direct retainer arm becomes passive when it is in its terminal position, with only the terminal 1/3 below the survey line. The direct retainer must meet these requirements, or retention is either not present or ineffective on the prosthesis. Maximum flexibility of the retentive arm is the greatest amount of displacement that can occur without causing permanent deformation of the clasp arm. The direct retainer is the only component of the RPD that contacts the surface of the abutment tooth apical to the height of contour. The flexibility of the clasp arms are dependent upon the length of the clasp arm, the cross-sectional shape of the clasp arm, the diameter, the longitudinal taper of the arm, the clasp curvature, and the material used to construct the clasp arm. The flexibility of a clasp arm increases as the length increases. With all other factors being equal, the longer the clasp arm, the more flexible it will be. There's a formula in your Stewart's text that gives you a mathematical explanation of the relationship of the length of the clasp arm to its flexibility. But in short, the flexibility is directly proportional to the cube of its length. By increasing the length, the horizontal forces imparted to the abutment tooth are reduced when that arm flexes over the height of contour into the undercut. Direct retainers should be tapered uniformly from their origin to their terminus. The recommended dimensions are, at its origin, a direct retainer on a molar should be approximately 2.5 millimeters in width and tapered down to half that width. A premolar would be approximately 2 millimeters in width at its origin and then tapered down to 1 millimeter at its terminus. The cast circumferential is measured from the point at which the uniform taper begins. The arrow in the upper right picture shows the area at which it begins. This area is called the shoulder of the clasp arm. The bar clasp is measured from the point at which its uniform taper begins, which is either at the minor connector shown in the middle picture or where acrylic resin begins as shown in the bottom picture. The shape of the cast circumferential affects the flexibility of the clasp. The flexibility of the cast C is less because its half-round form is in several planes. It can only flex in one plane, which is away from or toward the tooth. It will not flex toward the occlusal and toward the gingival area. The cross-sectional form of a clasp affects flexibility. The cast circumferential clasp has a curvature in more than one spatial plane. It has less flexibility than the wire clasp, which can have universal flexible form as shown on the right illustration. All those arrows are the directions in which a wire clasp can flex. For this reason, the cast circumferential is most acceptable on a tooth-supported removable partial denture. The cast C flexes only on seating and removal of the prosthesis toward the tooth and away from the tooth. On a distal extension or extension base RPD, the arm next to the distal extension must flex during placement and removal, but also during functional movement of the base, since that prosthesis is not supported at the posterior end. So the wrought wire would be a popular clasp to use on this type of a denture. The diameter of the clasp arm also affects flexibility. Clasp flexibility decreases as the cross-sectional dimensions increase. With all other factors being equal, The greater the diameter of the clasp arm, the less flexible it will be. Studies done on evaluating flexibility of the cast circumferential or half-round clasp show that the width to thickness ratio is ideal when it is a 2-to-1 ratio. Shown on the images at the bottom, it is recommended that the diameter of the clasp arm at the shoulder of the direct retainer designated D1 be 2 times the diameter of the arm where it tapers down at the terminus. Alloys with a higher elastic modulus are stiffer than ones with a lower elastic modulus. Chrome cobalt and nickel chromium alloys have clasp arms that are stiffer. If the practitioner wants more flexibility in the clasp, he would choose gold or a wrought wire. Gold is very expensive though, and it's not used very much today. Greater rigidity with less bulk is possible through the use of the cast chromium alloys. With gold, the bulk must be increased to obtain the needed rigidity. The wrought wire clasp is made by drawing a cast metal through a die. The elongated structure of the wrought wire makes it more flexible than a cast structure. It may recrystallize, though, if the following takes place. 1. If the wrought wire is heated, as is sometimes the case when the soldering is done very close to the shoulder of the wrought wire direct retainer, or 2. When the framework is cast to the wrought wire. The second way the clasp becomes less flexible is by doing something called cold working the clasp. This takes place when the wrought wire is adjusted or bent several times. The metal recrystallizes and makes it more apt to fracture. This is a chart comparing the flexibility of gold with chromium cobalt. You will notice with either metal that as the length of the clasp arm goes up, the flexibility of the clasp increases. You will also notice that the gold could go into a larger undercut than the chromium cobalt because it exhibits greater flexibility than the chrome cobalt for a given length of clasp. Type 4 gold will flex more than cast chromium alloys. The greatest undercut that we can engage with the cast circumferential and bar clasp is the 0.01 inch undercut with the metals that we use today. An alloy exhibiting a higher elastic modulus has greater stiffness, while alloys that display a lower elastic modulus have greater flexibility. The location and depth of a tooth undercut or retentive area exists only at a given path of placement that is determined with the use of the Dental Surveyor. The position of the cast on the Dental Surveyor cannot be changed during the marking of the teeth with the lead marker, or in other words, when you're surveying the cast. The point of contact of the analyzing rod or the lead on the tooth is the height of contour of the tooth at a particular path of placement. The area below the height of contour is where the undercut is located and will be the area that we use for retention of the partial denture. The position of the terminus of a direct retainer is determined with an undercut gauge placed in the surveyor at the path of insertion. We determine that we're going to use a 0.01 undercut gauge if a cast circumferential or a bar clasp is going to be used. If we are going to place a wrought wire direct retainer, then we would use the 0.02 undercut gauge. The undercut gauge is placed against the tooth, it's in the surveyor, and the point at which both the horizontal and the vertical rod touch the tooth, that is the point of 01 undercut or 02 undercut or 03 undercut. These are shown in the illustrations to the right. The cast circumferential clasp is a half-round shaped clasp that is cast with the framework. It engages a 0.01 undercut and is shown in the upper right picture. The wrought wire is a round wire that is soldered to the framework and engages a 0.02 undercut. See the middle picture. And lastly, the gold cast clasp can engage a 0.03 undercut and is cast with the framework, but it's rarely used today because of the price of gold. The retentive terminus for a suprabulge clasp should terminate at the mesial or distal line angle of the corresponding abutment tooth at the opposite end from its origin. It should ideally be placed on the facial surface of the abutment if the appropriate contours are present or can be made to be present by tooth alteration. The terminus is ideally placed in the cervical one-third of the tooth occlusogingivally, but no higher than the middle third. Direct retainers have to be flexible, so it tapers in width from its origin at the shoulder to its terminus. If the tooth is a molar, the origin will be approximately 2.5 millimeters in width and should taper down to 1/2 the size of the origin width at the terminus. Therefore, it would be about 1 to 1 1/4 millimeters wide. If it's a premolar, it will be 2 millimeters at its origin and taper down to about 1 millimeter at its terminus. The reciprocal component should be rigid. Therefore, it's more uniform in width from its origin to the terminal point rather than tapering. It is placed all above the survey line. It should be positioned to touch the tooth before the direct retainer. It is positioned ideally in the middle one-third of the tooth, occlusogingivally, and no higher than the junction of the middle and occlusal third of the tooth. It is never placed at the gingival margin. Reciprocation can be in the form of an arm or it can be in the form of a plating. The reciprocal arm should touch the tooth at the same time as the direct retainer, as shown in illustration on the left, so that it braces the tooth from movement in a lingual direction as the direct retainer flexes over the height of contour into the undercut. In illustration 2, if the direct retainer touches the tooth before the reciprocal component, forces are exerted in a lingual direction, causing the tooth to rotate and the tooth to be displaced to the lingual until that stress is equalized. Clasp encirclement is the characteristic or attribute of a clasp assembly that prevents the tooth from being able to move away from the clasp assembly. The clasp assembly must encompass more than 180 degrees of the greatest circumference of the crown of the tooth. It has to be more than halfway around. It passes from a diverging axial surface, sometimes referred to as the suprabulge or the support area, to the converging axial surfaces on the direct retainer side, referred to as the infrabulge area, the undercut, or the retentive area. The cast circumferential clasp usually encompasses the tooth by about 320 degrees, like we see on that upper picture. Now, on this lower picture, the clasp closest to you on the patient's right side, do you see anything missing there? There's a rest missing, and remember that a clasp assembly has to have the 4 component parts of it. If you don't know what they are, look them back up in this exercise. According to the principle of encirclement, when a bar clasp is used, the framework must have at least 3 widely spaced areas of tooth contact that embrace more than 1/2 of the tooth's circumference. The example in the picture shows this requirement being met. The picture on the left shows an error in the principle of encirclement. That clasp does not encircle the tooth properly. It is not more than 180 degrees of encirclement of the tooth, like the one shown on the molar abutment on the same picture. In the middle, a direct retainer arm is not supposed to look like an airplane that's diving to its death. It should look like the lower middle picture, where the outline form of the clasp follows the marginal gingiva form. It's like a ski jump. It goes down and then it rises at the terminus. The molar pictures on the right show a clasp that's too short on the top picture, and the correct form is shown in the lower picture. Passivity is the quality of an ideal clasp assembly that requires no transmission of adverse forces to the associated abutment tooth when the prosthesis is fully seated. The direct retainer arm becomes active when it flexes over the height of contour on its way to the undercut of the tooth. When it gets to that final position, it is passive. There are no lateral forces being exerted on that tooth. The only time the direct retainer arm may become active is when some dislodging force is applied to the prosthesis. If the clasp assembly is not passive, then the tooth may become very sensitive to the patient, or it may physically move. The clasp assembly must provide support. The rest that is placed on the abutment tooth in a prepared rest seat is used to limit the movement of the denture in a cervical direction and to transmit functional forces to the abutment tooth. The primary purpose of the rest is to provide vertical support for the partial denture, but it has other functions. One, it maintains the components in their planned positions, like the direct retainers and the reciprocal components. It also maintains occlusal relationships by preventing settling of the denture. It prevents impingement of the soft tissues by the framework, and it directs and distributes occlusal forces to the selected abutment teeth. Rest may be placed on sound enamel or on any restoration that has been proven scientifically to resist fracture and distortion when subjected to applied occlusal forces. Rests are primarily positioned on the occlusal surfaces of molars and premolars. You will also find them on the cingulum of maxillary centrals and canines and on the incisal surfaces of mandibular canines. They're usually given the name of the surface on which the rest actually is placed. The rests shown on all four abutment teeth on this example are called occlusal rests because they are placed on the occlusal surface. These are embrasure rests, or interproximal occlusal rests. There are two connected rests, one on each of two teeth that are adjacent to one another. Because this rest is placed on the lingual or the cingulum of the canine, it is referred to as the lingual or cingulum rest. You may also find this type of rest on the maxillary central incisor. The incisal rest is usually found on the mandibular canines. The cingulum is not well developed on the mandibular canine, and the enamel is very, very thin in the area that you would place a rest. So we resort to placing them on the incisal edge. Sometimes we do an acid etch cingulum rest out of composite and place it on the mandibular canines. Then it would be considered a cingulum rest. We like to place the incisal rest on the disto-incisal angle of the canine because it is a little less anesthetic, as it is a little more concealed from view. The incisal rests are not very aesthetic, and that's why we often do an acid etch cingulum rest on the mandibular canines. Sometimes because of occlusion, we may just place a fossa rest on the mesial or distal of the maxillary central incisor or canine. We then call it a mesial fossa rest or a distal fossa rest. The occlusal rest is placed in a prepared positive rest seat. The occlusal rest must be designed so that the movement of the clasp arm cervically is prevented by its use. This is the end of the Clasp Assemblies Lecture Part 1. Please go to the lecture titled Clasp Assemblies Lecture Part 2 for a continuation and conclusion of the Clasp Assemblies lecture. Have a great day today.